Hi everyone, and welcome back again. In this lecture, I will show you another iterative method which is called Gauss Seidel method that is used to solve a given systems of equations. And as you will see sooner, Gauss Seidel method is pretty close to the Jacobi method that we learned in our previous lectures. Alright, before giving you a concrete example, let's first define what the Gauss Seidel method is formally and the steps that we should follow to apply this method. Alright then, Gauss Seidel method is an iterative algorithm for solving a system of linear equations where our coefficient matrix is a square, strictly diagonally dominant matrix. So this is again an iterative method, which means that in each iteration we update the newly obtained values of the unknown variables, and in this manner we hope to reach to the very closest solution in the end. In other words, we hope that we would converge to the exact solution with respect to some error tolerance that we predefined. And one thing also important to note in this definition is, as you notice, we need to have a square strictly diagonally dominant matrix, and this is to ensure the convergence. So if this condition is held, then we guarantee that our method will really converge to the exact solution with respect to, again, some predetermined error tolerance. And what does it mean for a matrix to be square and also to be strictly diagonally dominant matrix? Let's first define that. Okay, and a square matrix, we know that a matrix is just a rectangular array that is arranged in rows and columns. And in this case, the number of rows and the number of columns may be different. And when the number of rows and the columns are not equal, then our matrix is in rectangular form. But in the case that we have an equal number of rows and columns, then we say that we have a square matrix. In other words, in a square matrix, the number of rows is equal to the number of columns. So this is one thing to ensure before starting to apply this technique. And the other thing is, we need to have a strictly diagonally dominant matrix. And what this means is, in terms of, well, if you want to define this formally, this is, if we have a matrix, let's first give an example. So suppose this is our coefficient matrix. Okay, let our coefficient matrix be defined like this. I put some values here, so say 5, say 20, say -3, alright, then -2, 8, and say 30. Okay, now as we all remember, we have the diagonal entries. If I draw this line, as you see, the entries that are passing through this line that I just drawn are called the main diagonal entries. These are diagonal entries because they lie on the diagonal of the matrix. And the definition says this: if we have a diagonal element, so, and in a generic form, say we have I, and here the first I from left to right represents the row number, whereas the second I represents the column number. And this means if we have an AII component, we take into account the diagonal entry. So this is actually a way to represent the diagonal entries. And the definition is this: for a matrix to be strictly diagonally dominant, each diagonal entry must be strictly greater than the sum of the absolute values of the other values in the same row. In other words, for instance, let's say we have A11. So what I mean, so we have A11. So A11 entry is the entry right here that I just circled in black. So it is 10. So its value is equal to 10. So this means 10 must be strictly greater than the other values, the sum of the other values. And we also take the absolute value. What I mean is, well, since these are positive values, I didn't need to take absolute values, but just let you know about that. So this means that I check to see whether or not this diagonal entry is strictly greater than the sum of the other values in the same row. So in the first row, I have 10 as the diagonal entry, and I also have 2 and 3 in the first row. So the diagonal entry must be strictly greater than the sum of the other entries. And this is held for the first row. And I do the same thing for the other rows. And each row has to satisfy this property to be strictly diagonally dominant. So for instance, for the first row, A11 should be strictly greater than the sum of absolute values of A12 and plus A13. I check to see whether or not this property is satisfied. And for the second row, again, the diagonal entry is 20, right? So for the second row of the diagonal entry is 20. So I check to see whether or not 20 is greater than the sum of the absolute values of the other values in the same row. So I take the absolute values of 5 and minus 3, which are the other values in the second row, and don't forget to take the absolute value, and the right hand side, the sum on the right hand side is equal to 8, but 20 is strictly greater than 8, so there is no problem for the second row as well. And at last I check to see whether or not this property is satisfied for the third row. And what is the diagonal entry in the third row? We have 30, right? We have 30 as the diagonal entry, so 30 should be strictly greater than the sum of the other values in the same row, which are minus 2 and 8 for this given matrix. So, and the right hand side sum is equal to what? It is equal to 10, right? So again, 30 is strictly greater than 10, and the third row also satisfies this property. And this is called a strictly diagonally dominant matrix. If there is at least a row that does not satisfy this property, then the matrix is not a strictly diagonally dominant matrix. So this is just to ensure that our Gauss Seidel method is really converging to a solution that we try to approach using this numerical iterative technique. So first, I look at the coefficient matrix, and I'm trying to verify that it is a square, strictly diagonally dominant matrix. If so, then I continue with my iteration process. If it doesn't, then this means that this method wouldn't work. All right, this is the formal check before starting our iteration. And how about the steps that we should follow in order to apply this technique? All right, let's get into that point. The very first step to take is, first of all, we should write each equation solving for its own variable. In other words, we rewrite each equation in the given system with respect to the corresponding unknown variable. So, for instance, if we have an equation like x plus y is equal to 10 and say 3x minus 4y is equal to 6, then I start with the very first equation on the top, and I isolate the first unknown variable x, and then move anything else besides the unknown variable x to the right hand side. And in this manner I would be able to isolate x and rewrite this equation with respect to this unknown variable, and on the right hand side I will have an algebraic sum. And for the second equation, then I continue in this manner. In the second equation I pick the second unknown variable, which is y, and then move anything else to the right hand side of the equality, and then I isolate y by dividing its coefficient, and I rewrite the second equation. And if I have many more equations, I will do the same. If I have 3 equations, then I do the same thing for the third unknown variable. If I have 4 equations, and do the same thing for the fourth unknown variable. Alright, this is the very first step. And then based upon this isolating process, I produce an iteration formula. Okay. And the second step, since this is an iterative process, I need a start point, which is called the initial guess. So if I have 2 unknown variables, then that means I will have 2 values for the initial guess. If I have only x and y as my unknown variables, then I need to start their values with something else. This is actually either a predefined value, or we just take the initial guess equal to zeros for all unknown variables. So if you are given an initial guess, we just use it. But if you are not given an initial guess to start the iteration process, then we just take this value for all unknown variables equal to 0. So if you are not given an initial guess for the first iteration, we take the values x and y equal to 0 and 0. So this is our initial guess. Okay, so this is our initial guess. All right, and in the third step, we update all variables with respect to iteration formula. And actually, the difference between Jacobi method that we learned previously and Gauss Seidel method comes out at this step. As you remember, in Jacobi method, actually we find the new values, newly obtained values in each iteration, and we use these values in the next iteration. But in the Gauss Seidel method, as soon as we find a new value for any of the unknown variables, we use that value in the same iteration. So we don't wait for the next iteration to come. Okay? In other words, as a new value is evaluated, then we just plug this value in the same iteration. Alright, and the fourth step and fifth step are same as we did in Jacobi method. We again compute the maximum absolute change of any component, which means that based upon the new values of the unknown variables in that iteration, we find the errors for each unknown variables and then take the maximum of them. And if this maximum error is less than our error tolerance, we stop our computational procedure. But if not, in other words, if the maximum of these errors is still not less than the desired error tolerance, then we keep iterating. And this means that we continue to iterate until we are done with the fifth step, which is actually saying that if we reach to the error tolerance, then we stop. Otherwise, we just keep iterating. So we repeat until the convergence is satisfied. Alright then. Having summarized the steps that we should follow and defined what the Gauss Seidel method is, now we can start solving a system using this method. And here's the way we apply this technique. So suppose we are given this system of equations. Alright, so 10a plus b is equal to 3. This is the first equation. And a minus 20b is equal to 5. This is the second equation. And our question is, solve the system using Gauss Seidel method we have just learned. And while doing so, we are required to take our error tolerance equal to 0.01. And we just predetermined this error tolerance. It is up to us, guys. So we can keep the error tolerance either smaller or larger. So it is our choice. And in this example, I just prefer to have an error tolerance of 1/100. Okay. All right. Let's apply our method after defining our problem. Okay, now we will try to converge to the exact solution by applying this Gauss Seidel method. And what is the very first step to take? Well, the very first step is in each equation we rewrite these equations with respect to one unknown variable and then try to construct an iterative formula that we can use. All right, so in the first iteration, what I need to do is I isolate the unknown variable a. So I move anything else to the right hand side besides a. And then I divide both sides by the coefficient of the unknown variable a, which is 10 in the first equation. And then what I get is I have a is equal to 1 over 10 times 3 minus b. And for the second equation, I isolate the second unknown variable, which is b, and then move anything else to the right hand side besides this unknown variable b, and then divide both sides by the coefficient of b, which is minus 20 in this case. And then I have a second rewritten equation. So I rewrite the second equation as well in terms of b. So b is equal to 1 over 20 times a minus 5. And this is actually the way how I will find these values, but don't forget one thing. I will not find these values only once. I will iterate through these formulas. So I need to somehow convert these equalities into the iterative formula, a kind of recursive formula that I can use in each step, in each iteration. And the way to do so is what? So here's the thing. So suppose I'm in the very first iteration. Then if I want to write this equality in the iterative form, then what I need is just an upper index, which I use here. And the power k is actually used to represent the number of iterations. So a to the power of k plus 1 is nothing but a tool that represents the number of iterations. If I take the value of k is equal to 0, that means we have a to the power of 1, which actually stands for the new value of the unknown variable a in the first iteration. And how can I find that? Well, on the right hand side, what I have, as you see, 3 minus b to the power of k. And when k is equal to 0, I use the first value, the initial guess for b, and then compute the new value of a. And up to this point, everything is the same as we did in Jacobi method, but at right this moment, something starts to change. Look at very carefully actually how we update the value of b in the first iteration. Okay, I am trying to find the new value for the unknown variable b, but be aware of one thing. I don't use the older value of a here, you see, a to the power of k plus 1. But a to the power of k plus 1, when I take the value of k is equal to 0, is actually the value we have just found above, right? This is the value that I have found here. So in the same iteration. So I use the value of the unknown variable a, which is newly obtained, right in the same iteration. I don't wait for the next iteration to come. In the Jacobi method, as we remember, I use this newly explored values in the next iteration and not in the same iteration. But in Gauss Seidel method, as soon as I find a new value for any of the unknown variables, I just plug it in the formula. Okay, this is very important. So let's start our computation after expressing these iterative formulas. Okay, our initial guess, since we are not given an initial guess, then what we do is, well, we take the values of all the unknown variables equal to 0. So the first value of a is chosen as 0, and our initial guess for the other unknown variable b is again 0. So this is the very first values of our unknown variables. And then we plug them in the formulas that we just produced above. So if you take k is equal to 0, then I put the value k is equal to 0, and I try to obtain the value of the unknown variable a in the first iteration. So it is nothing but 1 over 10, 3 minus 0, and why 3? Because 3 comes from the formula that we just produced above, right? We rewrite the equations and we have 1 over 10, 3 minus b to the k, right? So I just put that values here, and I found the new value for a. And I do the same thing for b, right? But be careful about one thing, which is very important, actually, which is the difference between the Jacobi method and Gauss Seidel method. You see, 1 over 20, that's fine. We have nothing to say about that. But here, just I want to bring your attention to this point. We use the value 0.3000, which is the value I just found in the same iteration for the unknown variable a, right? We just found it above here in the same iteration, and I just plug that value here. So I don't wait for the next iteration to come to use this newly obtained value. I plug it in the formula as soon as I find it. Okay. And then I compute the value of b. And what we are going to do now, all right? Now I have the newly obtained values for two unknown variables a and b, and now I look at the errors. So how can I find these errors? All right, that's simple. That's the same as we did in Jacobi method. Again, in the two successive iterations, I just compute the absolute value of the differences of the unknown variables values we found. So our initial guess for the unknown variable a is 0, and the value of the unknown variable a at the end of the first iteration is 0.3. So I just take the difference and I take the absolute value, and look what I have found. So 0.3000, this is the error for the unknown variable a. And I do the same thing for the unknown variable b. So the value of b with respect to the first iteration, in other words, based upon the results we obtained in the first iteration, is minus 0.2350. So the initial guess for b is 0, and I just take the difference and I take the absolute value. So don't forget to take the absolute value. We look at the absolute values. And what we see here, okay, we have 0.3 error for the a, and we have 0.23 error for the b. And then I just take the maximum of this, which is actually called the infinite norm, if you remember. And why I take the maximum of this? Because if the maximum of these errors is less than the error tolerance we just assumed, then the other errors should also be strictly less than the error tolerance, right? That's why we take the maximum of these errors. Alright, and as you notice, we don't have an error that is less than 0.01. So I prefer to have an error tolerance here, as I circled in black, 0.01. But each error rate is greater than this value, so we are not satisfied with the error tolerance. And this means that we continue to iterate. So because we have not been able to reach to the desired error tolerance. And in the second iteration, I find the values again with respect to this iterative formula. And for the a, I use the value 0.3, and then I find the new value of a. But for the b, again, don't forget to use the value of a that we have just found in the second iteration. So in the formula of b, we use this newly obtained value of a. And again, after finding the new values of each unknown variable, we compute the error rates in the same manner. So we just take the difference of these values of the unknown variables with respect to the successive two iterations. In other words, the value one step before and the value we obtained now in this iteration. We take the difference, we take the absolute values and select the maximum of these errors, which is 0.235, and it's still not less than 0.01. So with what this means is we still haven't been able to reach to the desired error tolerance, and then we continue to iterate. And in the third iteration, we again compute our new values and calculate the errors, of course, using our calculators, and then find the errors. And then select the maximum of these errors. And in this case, as you notice, the maximum of these two errors is 0.0001175. And as we see now, we're done with error tolerance because this error is strictly less than the error tolerance we assumed. So our error tolerance is 0.01, and our maximum error that we have in the third iteration is less than this value. Then this means we stop here. Okay, and that's the end of our computational procedure to apply the Gauss Seidel method. And what is our solution? And it is simple. We produce our output. What is, and our output here, right, you see, we produce our output with respect to the obtained results in the third iteration. In other words, in the last iteration, where we stop. When we stop our computation, that means we find our approximate solution with respect to the desired error tolerance. And in this case, the newly obtained values of both unknown variables A and B are our solution, right? This is our solution, and we converged to the solution. And of course, if you choose even a smaller error tolerance, we can continue to iterate. Or if we use a larger error tolerance, then we can stop our computation earlier. It depends also on the way that we choose our error tolerance. Okay. And one thing to notice here, actually, if you see that, well, in the very first, we start with the values of 0 for each unknown variables, and in the end of the first iteration, we find 0.3 and we find 0.23 for each unknown variables respectively. And then, as I continue, you see that we approach actually to some values for both unknown variables while we reduce the errors. So actually we try to satisfy the error tolerance while we are converging to the desired output, which is actually our exact solution. And one thing, if we want to solve this equation, what we need to do is just multiplying, for instance, the second equation by -10, and then finding the solutions for each unknown variables. Then we have actually the exact solution here. So this is our exact solution. If you want to solve this equation by using elimination technique, then we have A is equal to 0.32, well, let's make it a little bigger, 33 and 83. And if you notice, this is the exact solution for the unknown variable A, and just compare it, it's almost the same. In other words, if I take the very first 2 or 3 digits, it's all the same, right? So almost there is no difference. But if I want to take more decimal points, then there will be a little error. And for B, so actually I'm writing the exact solution to let you see that we really converge to the exact solution, and we are almost there. We are in the neighborhood of our solution with a desired error tolerance, and B is equal to the exact solution. B is equal to actually minus 0.23, 38, and 30. And if you notice, they are almost the same, right? If we take the first 4 or 5 digits, then we actually find the exact solution, as you see here. It is very clear to observe that we really converged to the desired result. Alright guys, this is actually what Gauss Seidel method is and what we should check before applying this technique, and I also explained to you the steps that we should follow to apply this technique, and also we see that we really converge to the solution and we applied all the numerical steps clearly. And that's it for this lecture, and see you in the next lecture.